So today I'm going to talk about transistor series voltage regulator. So this, as you can see, the circuit diagram for transistor series voltage regulator. This is called series voltage regulator because this BJT Q1 is connected in series with the load, and that is the reason why it is called as transistor or BJT series voltage regulator, because this transistor is regulating the constant output voltage, and this transistor is connected in series with the load. If this transistor Q1 is connected across the load or in parallel with the load, then we call it as transistor shunt voltage regulator. So let me explain you first the circuit in brief, and then I will do some kind of simulation, will show you some results. And this circuit is really very useful for the constant voltage regulation. As you can see that this is my supply voltage, then I'm having a reverse voltage protection. I used here diode D2. Then this R7 is used to control the current flowing through the Zener diode, and this through the base of this Q1. Then R3 I use to distribute the power, to take some power away from this transistor Q1. So that's why I use the R3. If you want, you can use, or if you don't want, if you have enough space on your PCB, then you maybe you don't need R3. But in my case, I need. That's why I used it. Then here R6 and Q3, they are in combination, and this Q3 and R6 is used for the overcurrent protection, or we can say so that used for in case of the short circuit at the output load, across the output load, then this circuit is activated. This combination of R6 and Q3 get activated, which means that as soon as there is a voltage around 0.7 to 0.9 volt across the base emitter of Q3, this circuit is activated. So as you can see that, for example, we have I'm having a resistance of R6 of 20 ohm, which means that when around 30 to 40 milliampere will flow through this R6, then the voltage drop across the R6, which is base emitter of Q3, around 0.6 to 0.8 volt, and that is enough to activate the Q3. So later on I will show you, I will do here short circuit across the R2, and then we can see that, you can see that here the current, what is exactly the current is flowing, maximum current is flowing through R6, and when this transistor is getting activated. Yeah, so here power supply which I used is linear power supply, which means that from 0 to 30 seconds the voltage will rise from 0 to 30 volt, and I'm having a temperature from minus 40 till 150 degree, just for my calculation. If you want, you can take it. If you don't want, you can't, as you wish. And then there is this transition time which I put here for around 30 seconds. So let me explain the functionality of the circuit. As you can see that, maybe if you want, I mean, just forget about this circuit. So uh, this is a very simple circuit. As you can see that this load R2 is connected across this transistor Q1 and the diode D1. This is a Zener diode, and the output voltage will depend on this Zener diode voltage and base emitter voltage of Q1. So which means that V output will be equal to the this reference voltage, Zener voltage minus VBE. And as I said previously, that this R7 is to protect the Zener diode from getting damage. That's why we used here R7, and also to control the base current of the Q1. Yeah. So function is very simple. As soon as you apply the input voltage here, V in, let's say when you apply the linear voltage from 0 to 30 volt, then at some point. Here I used 3.3 volt Zener diode. You can use also the bigger one as you wish. So this 3.3 voltage minus 0.6 or 0.7 voltage for base emitter of Q1, which means that 3.3 minus 0.6. So at the output we will get something around 2.7, 2.8 volt. Yeah, 2.5, 2.6, 2.7 volt, and that will be constant for at the room temperature. But as the temperature changes, this output voltage also fluctuate. But the good point here is that the temperature coefficient of this Zener diode for the low range work against the temperature coefficient of this transistor. So which means that they work against each other, so they compensate each other. So the output voltage what we get here is more stable. So let me do the simulation here. For example, as here this is V in, as you can see that from 0 to 30 volt in 30 seconds. And then let me check here. So as you can see that that there are so many curves, and the reason behind that is because of this temperature. If I will remove this, then there is only one curve. Yeah. So let me just zoom this. So here, as you can see that how the temperature, how the voltage changes from 2.9 volt till 3.3 volt. Yeah. So it's for the different temperature. Then this is the output. As you can see that this V out, and V out is, as I said previously, it's between 2.5 to, yeah, it's quite stable, 2.5 volt, which means that this base emitter voltage should be around 0.6, 0.7 or 5 or 0.78 volt. So let me check this. Yeah, 70.8 volt. The maximum and the minimum is 0.45 volt. Yeah. And the current which is flowing through the 1000 ohm resistance is around 2.5 milliampere. So let's say for 20 milliampere I need 270. Save, simulate this. No, 270 is less, so let's say 180. This is what I want for my circuit. Yeah, so it's around 14 milliampere, as you can see that. Yeah, 12.88. Yeah, so that's how it is. So here, as you change the load, the current will change, and at the output you can see that the voltage is quite stable. It's in between 2.2 to 2.3 for all this temperature range from minus 40 till 150 degree. Yeah, so let me do some calculation and change this value again to 1000 R. And as I said previously, let me show you. For example, if there is a short circuit between at the output, then how this circuit works. So I shorted the output, and now as soon as I shorted the output, at the output you can see that there is no voltage, or sorry, I have to save this first, sorry. So now it's saved, and as you can see that there is no voltage. But here you can see that how much current is flowing. It's something around 36 milliampere. Yeah. So it's in between 22 to 36 milliampere. So depend on the temperature, at which temperature you are operating the circuit. And if I will see this base emitter voltage, so you can see that the base emitter voltage is in between 0.45 till 0.77 volt, which means that when there is here is short circuit, then only this circuit is working. Yeah. And so that's why the voltage here is 0.8 volt, and at the output, as the output is shorted, so definitely obviously the voltage will be 0. Yeah, so let me remove this, and so let's do some calculation here. Let me explain you some calculation here. As you can see that the output, let me remove this. As you can see that here the output voltage, this output voltage is dependent on this Zener reference voltage and the base emitter voltage of Q1. If your output voltage get increased, which means that your output will only get increased when your VBE base emitter voltage is less. Only in that case your V output will be more. So as soon as your VBE get reduced, the current flowing through the transistor will get reduced, which means that your V output will automatically get reduced, and vice versa. For example, if your V output will be less, which means that is less only when VBE is more. When I'm saying that VBE base emitter voltage is more, then I'm talking the range between 0.6 to 0.8 volt or 0.9 volt, not more than that. So if your V output is less, which means that your VBE is more. If this is more, then what will happen? The transistor will, when the base emitter voltage will be more, the transistor conducts in a better way, or transistor will also conduct more, which means that automatically at the output you will get more voltage. So that's how it balances keep the output voltage constant. Yeah, so let me do some calculation here. Let me show you some calculations, and then yeah. So for example, if you have to design the circuit and you want to calculate the output voltage, what you can do, you know that you can take this, for example, for 10 volt. Choose this 10 volt. So you have a Zener diode of 10 volt, and VBE, I took it 0.65. So 10 minus 0.65 is around 9.35. That should be the voltage I'm expecting here. So let me simulate this and see at the output what I'm getting. Just let me tell you one more thing. For example, this time, I took the time in my time scale same as the voltage scale, which means that I can also take it as a voltage. So for example, let's take about 12 volt or 13 volt. Yeah, so here, so as I can see that the voltage I'm getting is 8.945 for the lowest voltage, and the maximum voltage I'm getting is 0.916. So this is because of the effect of the temperature here on your Zener diode and on the value of base emitter voltage. So that's why theoretical values are not always correct. If you don't consider the temperature effect, then definitely you will get these values, or maybe you will get something around in between. Okay, anyway, so for example, as you can see that output voltage is 9.35 volt, and the current flowing through this will be equal to then the voltage across the resistance divided by the the value of the resistance, which means that the voltage across was 9.35, and when you will divide with this 1000, so 9.35 milliampere. So let me check the current at 13 volt. So it's around 8.944 is the minimum value, and the maximum value is 9.16. So yeah, as I said, that is because of the temperature, but I took it at 13 volt. As you go as you see at the 18 volt or 30 volt, then the values, for example, these values are changing for the current. Now, one more point, that's how you can calculate the current, what is flowing through the at the output of your load, and the voltage across your load, and you can check whether it's giving the constant constant voltage. Oh, sorry. Yeah, so you can check that whether it's giving constant voltage at the output or not. One more thing I would like to bring into your notice, and that is, for example, the I just checked here. As you can see that this is the model for the Zener diode, and in this Zener diode, I didn't find any temperature coefficient compensation parameter. It's not included because the parameter, that parameter is called something like TBV1, and then I've looked into the SPICE model from the LT SPICE standard diodes which are available here. You can see that, and which is called TB1. So as you can see that this TB1, which means that here, let me show you. Yeah, TB1 is the linear breakdown voltage temperature coefficient. If this parameter is added in this model of the Zener diode or transistor, then it will compensate compensate during the temperature the value of the value, how do we say, then it will add or subtract the value in your nominal voltage as per the temperature changes. For example, if it is 2 millivolt per degree, then after every degree it will increase or decrease the voltage 2 millivolt. But as you can see that here this TB1 is available only for some particular model and not all the model. So here this is available for IN 756 and 752, for example, here TB1, but the rest of the BZX 38 and all this series, I didn't find this parameter, and the only which what I found is for just let me show you here for this Philip models. As you can see that here, these three models, there they added this parameter. Yeah, and the rest, for the rest, as you can see that this parameter is not added, and so that I will also show you here. For example, if I have chosen here 10 volt Zener diode, and if I will click here, then you can see that for example the voltage is around 10.08 and 10.06. So here I took the temperature from minus 40 degree till 150 degree, and if my nominal temperature is 20 or 25 degree, let's take the nominal temperature, and then I'm having a difference of around 150 minus 20, which means that 125 degrees. And if there is normally the temperature coefficient is between 2 to 5, so it also depends on the component, type of component what we have, Zener diode or BJT or diode, but normally it's between 2 to minus 2 to minus 6, and it also depends on the minus 2 to plus 6, millivolt per Kelvin. So That I will prove you. I mean, as you can see that, for example, if it's 125, the difference here from the room temperature till maximum temperature is 125 degree, which means that 125 multiplied by, take in this example, for example, 2 millivolt plus 2 millivolt. So it's something around 125 into 2, which means that how much is that? 250 millivolts. So this voltage should be in a difference of at least 0.3 volt, 0.25 volt. For example, if this is 10 volt is the nominal, then it should be like 10.2, somewhere here, 10.10 to 10.25. But as you can see that parameter is not added, and so that's why there is no effect of that. So let me take you to the let me take the another model, and that model is where we have seen that TB1 was added here. For example, here they have added TB1 in this Zener, that we can take, or we can take also here that 3.3 volt from the Philip here, this TB1 minus 46 micro. So once I have chosen that, and when I will save and then simulate, and then let's go here. So you can clearly see that for this temperature range, the voltage changes from 3 volt, as you can see here at the corner, exact value 3 volt, and then when I will go for the maximum, then it's around 3.39. So here the temperature compensation is working perfectly, but for the 10 volt or the another values, it's not working. So just when you are doing the simulation, then be careful about such kind of things, because you expect that it should compensate, but it's actually that parameter is not added in the model, so that's why it's not compensating. Before I go, I have one more thing I would like to add, and that is for example, if you are using if you are working in a company, I mean, where you have to reduce the cost of your product, and you are using kind of a voltage regulator which costs you something around 30, 40, or maybe 60 cents. So this circuit is really very useful. And as you can see that it's also very economical circuit. So here you have a solution for this voltage regulation, for the voltage regulator, around in 10 to 12 or maximum 15 cents. So you can save a lot of money, and such kind of circuits are really very useful for the sensors supply voltage, because sensor or for for the circuit of like LEDs and so, because they don't need much more current. So 10, 20 or 30 milliampere, even you can, with this circuit you can generate till 100 milliampere. That is not an issue here. So that's how you can design the series voltage regulator. If you like the video, then please subscribe the channel, and thank you very much.